Welcome to this explainer. Today, we're diving straight into the hidden layer of the modern internet. We're going to explore the precise architectural strategies that keep high availability web applications running smoothly, preventing them from crashing under those massive, unpredictable traffic spikes that can literally cost millions in downtime. So, have you ever wondered how exactly the biggest apps handle millions of concurrent requests without their servers just completely buckling under the pressure? Well, the secret sauce is highly effective load balancing. Okay, let's look under the hood and see exactly how this magic happens. Here's our roadmap for today. We'll start by zooming in on the micro level with Layer 4 versus Layer 7 routing. Then we'll tackle the sticky session dilemma. After that, we've got a software showdown, HAProxy, NGINX, or Envoy. Then we'll zoom all the way out to macro-level infrastructure with cloud-native versus cloud-agnostic setups. And finally, how to make the right choice for your stack. Let's get right into it. Part 1, Layer 4 versus Layer 7, the absolute foundations of traffic routing. Think of this whole thing kind of like a giant mail sorting facility. Layer 4 operates at the transport layer. It's like a postal worker who only glances at the outside of the envelope, the IP address and port, to route it blazingly fast. It is totally blind to what's actually written inside. On the other hand, Layer 7 operates at the application layer. This is the worker who carefully opens the envelope, reads the letter, and makes a highly intelligent routing decision based on the actual content, like HTTP headers, specific URLs, or cookies. It requires a bit more computational overhead, sure, but it gives you that incredibly powerful context-aware routing. Moving on to Section 2, the sticky session dilemma, and keeping your users connected. While load balancers are great at distributing traffic, sometimes you actually need a user to stay exactly where they are. Imagine you're online shopping, you've spent an hour building this massive cart, and suddenly it's totally wiped out just because you got bounced to a new server. Frustrating, right? That's what sticky sessions, or session affinity, solves, by pinning the client to a single backend target. For apps that store session state locally on the server, think active shopping carts, user-auth tokens, or in-memory caches, losing the connection to that specific server means your user immediately loses their data. Now, what's really interesting about this process is how elegantly simple duration-based cookies are in action. Let's say you're using an application load balancer. The very first request hits with no cookie at all. The ALB routes it to instance A, and then injects an AWS ALB cookie right into the response. From that moment on, every subsequent request carries that cookie. It acts like a VIP pass, telling the ALB to bypass standard distribution and route directly back to instance A. But there's always a catch. The trap here is uneven load distribution. If a handful of highly active power users, the ones absolutely hoarding all your CPU, all happen to get pinned to instance A, that server is going to melt down while instances B and C just sit there twiddling their thumbs. Plus, if autoscaling suddenly removes a target during a scale-in event, those sticky sessions instantly break. And that is exactly why moving to a stateless design, where session data lives in a shared database or a Redis cache, is the ultimate architectural goal. All right, Section 3, HAProxy, NGINX, or Envoy, the software showdown. If you're self-hosting or managing your own proxies, you're definitely looking at these three heavyweights. HAProxy is built on a single-threaded, event-driven architecture. It's practically the gold standard for pure, dedicated load balancing and high availability. Then you have NGINX, which utilizes a multi-worker asynchronous model. It's incredibly versatile and often pulls double duty as both a web server and a reverse proxy. Finally, there's Envoy. Written in C++, this is the modern darling of cloud-native environments, built specifically from the ground up for microservices and complex service mesh architectures. And the data brilliantly illustrates the raw performance differences here. When put to the test on a standard 4-core virtual private server, HAProxy easily pushes past 50,000 requests per second. Its single-threaded nature ruthlessly eliminates context switching overhead, making it the undisputed champion for pure HTTP/1.1 throughput. NGINX holds incredibly strong at 40,000, while Envoy, which does require a bit more memory and CPU overhead for all its advanced features, sits at around 35,000. But hey, raw speed isn't the whole story. If your modern web apps require HTTP/3 and the quick protocol to reduce latency, NGINX is the clear winner right now. They've had mature support for it since version 1.250. Envoy, on the other hand, currently treats HTTP/3 as experimental, but it completely dominates when you need distributed tracing and automated mutual TLS in zero-trust environments. Now, managing all this software yourself takes a ton of engineering effort, which is why so many teams just default to the managed services provided by their cloud vendors. But there's this major pain point in the industry known as the 80% rule. Native load balancers cover about 80% of your basic use cases, but they frequently lack critical capabilities. We're talking things like advanced web application firewall customization or really complex traffic mirroring.
Which leads us perfectly into Section 4, Cloud Native versus Cloud Agnostic. The infrastructure battle. When you look at the big three providers, you quickly realize they approach traffic with completely different philosophies. AWS provides unmatched deep integration with their own compute layers like EC2, ECS, and Lambda. But their application load balancers are regional by default. If you want to go global, you have to bolt on their global accelerator. Azure excels in Active Directory integration and hybrid Windows environments, but its routing is somewhat fragmented between the global front door service and the regional app gateway. GCP actually stands out quite a bit here. It utilizes a unified global control plane and gives you a global Anycast IP right out of the box. So the crucial point is this ultimate trade-off. Cloud-native solutions offer this incredible one-click convenience. They're fully managed, pay-as-you-go, and they scale automatically. But they build a cage of severe vendor lock-in. You absolutely cannot just lift and shift your complex AWS routing rules over to Azure. Cloud-agnostic third-party solutions, however, run exactly the same way across all your clouds and even on-premise data centers. They offer consistent advanced packet inspection, unified WAF policies, and completely avoid that lock-in. Finally, Section 5, making the right choice for your architectural dilemma. So how do you actually decide? Here is a practical framework to act as your guide. First, assess your vendor lock-in risk. Is a multi-cloud strategy something you'll need in the future? Second, evaluate your high availability needs. If an entire cloud provider goes offline, will a cloud-agnostic setup be the thing that saves you? Third, look really closely at the cost models. Cloud vendors charge by load balancer capacity units, or LCUs, which scale linearly with your traffic and can literally cost millions at high volumes. Third-party solutions often use a bring-your-own-license, flat-rate model instead. Finally, analyze your security. Do you need one unified security wall that acts the exact same way, regardless of where the server is actually hosted? Ultimately, you have to look closely at your specific stack and weigh that convenience against control. Which leaves us with one final provocative thought. When you examine your infrastructure today, is your load balancer actually solving your traffic problems, or is it silently creating brand new ones? Thank you so much for joining me for this explainer. I hope this helps you optimize your infrastructure for absolutely whatever traffic comes your way.